In this lesson, we're going to be looking at rules for definite integrals so that we can solve integrals. First, this is the table of rules that we have. This is in your book. Looking at these one at a time, the first one's talking about the order of integration. Notice that if our order is given to us backwards, like if we're going from B to A instead of A to B, we can turn that around. It would be the same thing as having a negative here. And what's happening is if I have this one right here, that would be defined as A minus B, which in this case, since B is on the right, this is going to give me a negative number. If I want to switch it around then, with this order of integration, my x's here, changing the order would then have an opposite sign of whatever I had. The second rule tells us what to do if we're going from A to A. So if I'm going from A to A, that means I only have one value. So for example, if I'm going from 3 to 3, there is no change. If there's no change there, I have no width to my rectangle, there can't be any area, I get a 0. A constant multiple looks something like this. If I have f of x and I double it, notice that each one of the rectangles that I'm taking for any one of these sections would just be double. So if this had maybe a height of 3, then now doubling it would make a height of 3, so I have a height of 6. Or maybe somewhere else, maybe over here it's 2, so I double it. This would also be 2. I have a height of 4. So each one of these rectangles is being doubled. So if I look at the area as a whole, then the area down here, when I double f of x, 2f of x would double the area. This would also work if I had a negative number, because that would just be a constant multiple of negative 1. So what it's saying is we can take our constant multiple, if we have a function and we have a constant multiple, we can just pull it out, we can calculate the integral on its own, and after we calculate it, then we multiply by the multiple. For sum and difference, we're looking at having two different functions here, f of x and g of x, and then adding them together. What it's saying is if we add these two together, we'll get another function here. So in this picture, I might have something that looks like that, f of x plus g of x. And I want to find this whole area here. But what I can do is I can split that up. Since we're adding those two together, then it would be the same thing as taking this area here, f of x, and just adding it on top of g of x. And so I can split this up and do it in separate parts, and that would be the same for positive or negative. So anytime we have two functions added or subtracted, we can just split it into two different integrals. The next one is additivity. It's looking at having two different integrals. One's going from a to b, one's going from b to c. Now notice this is the same, and that's important in this one, because if I'm finding the area, first of all, from a to b, and then I'm finding the area from b to c, notice we could just add all those together. This would be the same as the area going the whole way across from a to c. So we can combine that into one integral, or sometimes we might want to go the other way and actually split it into two integrals. Next, let's work a few of these out using the rules that we just learned. Looking at this first one, we're going from 4 to 1, but our given integrals, the ones that we know values for, are going from negative 1 to 1, 1 to 4, negative 1 to 1. Notice this one's h of x instead of f of x. So if I want to go from 1 to 4, that would be okay for this one, but my order is wrong here. I need to go from 1 to 4. Now in order to do that, I will need to make this negative. So I have the 1 to 4 f of x being negative 2, and that was the negative of this, so I'm going to get 2 from that. In the next one, we have negative 1 to 4. Notice that's a problem. This goes from 1 to 4, but this one goes from negative 1 to 1. Now since these values are the same, I can actually put this all together and combine it so that if I'm going from negative 1 to 1 for f of x, and add that to 1 to 4, that would be the same thing as going from negative 1 to 4, because I have that overlap for those two parts. And so looking at the values that we have for negative 1 to 1 for f of x, we have 5. And from 1 to 4, we have negative 2. And so we get 3. For c here, notice we've got f of x and h of x. First of all, we have a sum here, so let's split this up. We'll say, first of all, that we have negative 1 to 1 for 2 times f of x dx plus negative 1 to 1. We keep the same limits of integration here as we split it up. Then we have constant multiples involved here. So I can pull that out for each one, negative 1 to 1, f of x dx. I can pull the 3 out. And then we substitute the value. So for f of x going from -1 to 1, that would be 5. And for this one going from -1 to 1, we would get, for h, we get 7. That's going to give us a value of 31. In this next set of examples, we have a little bit of a problem. Notice the first one's asking us to go from 0 to 1. But we don't have any information about what's happening at 0, so we don't have enough information to do this one. This is not possible based on our given information. This one we're going from -2 to 2. Again, we don't have anything about -2 to 2, and we can't make any assumptions about what should happen based on these numbers. If we don't have the exact values, we won't be able to work these out. For the next one, if we look, we're going from -1 to 4. And notice for f of x, we could go ahead and split that up. So if we were going to split this up and thinking about f of x dx, since I have a plus here, I can split this into two different integrals. And for f of x, we can actually split this up, but we could work the f of x part out by going from -1 to 1 and then going from 1 to 4 for f of x. The problem is with h of x, we only have -1 to 1. We wouldn't be able to work out the part going from 1 to 4 for h of x. It's not possible to work out this whole integral because this part we don't know. The next rule is the maximum or minimum inequality. And what this one's looking at is if we know the maximum value of f of x. Okay, so here I've got my integral going from a to b for f of x. That's my blue graph here. If I know the maximum value of that, I've got that right here, my maximum value, and I know the minimum value of that, then if I take this part saying I'm taking the minimum value times the interval, basically that's taking this rectangle here, looking at that minimum value. And so finding the area of that rectangle that's based on going from the axis up to my minimum value, that has to be less than my whole integral, or maybe equal to. If I look at the maximum value then, up here, and create a rectangle using that, going from a to b, that rectangle would have to be larger than the whole thing if we're using our maximum value. So I know that I have to be sandwiched between those two values. If I know that my graph of f of x is always greater than g of x, so I've got my f of x here, always greater than g of x, on the interval from a to b. Now that is important. I might get lower somewhere outside of the interval, but that's not actually part of what I'm doing here. But inside that interval from a to b, since f of x is always greater, then that area would also be greater than g of x everywhere. Now notice that these formulas, these rules, are going to work whether these values are positive or negative. Okay, so even if I'm negative, I would still get larger values here, and that's going to be true for all of the ones that we just looked at.